All right, so today we're going to continue with our logarithm discussion and talk about their graphs as well. So let's start with graphing some exponentials. So let's kind of get our brains in the exponential graphing realm. This question looks like a lot is going on, and I suppose that there is, but it all comes from this parent function of y equals 4 to the x. And so I know very quickly this is at 1. Move over 1, I'm going to be at 4, and this is at a fourth. So I know this is the graph I'm starting with. I'm obviously shifting it, and I'm shifting it. And then, what else am I doing? I am flipping it upside down. So now it's here. And then the half is a vertical scale change. So whatever distances I was going to do, I'm now going to do half of those distances. So it's going to end up compressing it once it flips over. All right, so just pay attention and you should be fine. So let's shift it -5. 1, 2, 3, 4, 5, and down 3. 1, 2, 3. So here is my new XY axis. This is an exponential graph, so it has a horizontal asymptote. So I know I can now ignore the 5 and the 3, and now I just need to figure out the rest of it. So normally I'd be up at 1, so that would go right there. But now I'm going to be at a half, and it's going to be flipped over. So instead of that point, I'm going to be upside down at 1 and then shrink it by a half. Normally, I'd be over 1 and up 4. 1, 2, 3, 4, right? Because it's base 4. So now instead, I'm going to be half of that. So it'd be down here at 2 instead, except it's flipped over. So that means I'm going to be over 1, not down 4, but down half of 4. The next point would be over 2 and up 16. So now it's going to be over 2 and down 8. 1, 2, 3, 4, 5, 6, 7, 8. Normally I'd be over 1 and up a fourth. So now I'm going to be down and it's going to be an eighth. And so I've got my graph that looks just like it normally looks, just kind of compressed down a little bit. And if I need to, I should be able to label these points. That one I can just count. It's 1, 2, 3, 4, 1, 2, 3, 4, 5, -4, -5. This point is down a half. 1, 2, 3 and a half. So 1, 2, 3, 4, 5. So -5, -3 and a half. And this one is down an eighth. So down 1, 2, 3, and an eighth. So -6, -3, and 1/8. All right, and let's try what appears to be a harder one. Ooh, we got a lot going on here. We've got this scenario again where we have not a 1 in front of as my coefficient on x. So the first thing I'm going to do is I'm going to rewrite this problem. And I've got a -3 times 1/2 to the factor out a -2, leaving me with x minus 2 plus 2. So I'm going to check that. -2 times x is -2x. -2 times -2 is +4. So this is correct. But, man, I don't want to graph that. So let's deal with this another way. Let's do some simplifying. This is a half raised to this power. So there's nothing stopping me from just making this problem a little bit easier. So let's turn a half into whatever a half to the -2 power is, which would flip upside down and become 4. And then we're left with x minus 2 plus 2. So this is really just going to be very similar to the last one. I've got my base function of 4 to the x. It's going to shift around, but it's going to be upside down and then stretched. So that means it's just going to be, the distance here is going to be bigger, 3 times bigger than it normally is. So let's get it in the right spot. What do we decide? We're going over to +2 and +2. So my axis system is now here. I've got my asymptote here. And let's graph our picture. So normally I would be up 1 at the y-intercept, but now I'm going to be upside down and 3 times as big. So 1, 2, 3. Normally I'd be over 1 up 4. So now I'm going to be over 1 from that and down 12, which 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then normally I would be at a 4th up, and now I'm going to be down 3/4. And I get a graph that looks like this. Asymptote at y equals 2. I can count these points out nice and easy. I'll just skip that. This point, however, let me practice. I am down 3/4. That's 3/4 off the asymptote. So that means I am at 1 and a 4th. So this point should be 1, 1 and a 4th. Okay, hopefully that all makes sense. Example number 1. All right, so we are going to graph 3 to the x, nice and simple. So that's going to be at 1, at 3. I'm going to do one more at 2, it would be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This will be at a 3rd, this would be at a 9th, a 27th, and practically 0 moving on from there. Let's label these points. This is 2, 9. This is 1, 3, 0, 1. This is -1 and a 3rd. And let's do one more. This is -2 and a 9th. All right, now what we want to do is we want to graph the inverse of this function, and graphing the inverse should be as simple as just swapping the x and y values, because that's what an inverse does. It swaps the domain and range. So let's go ahead and do that. 0, 1 becomes 1, 0. 1, 3 becomes 1, 2, 3, 1. 2, 9 is 9, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 2. If I was going to keep going, I would have over 27 and up 3. If I want to go one more, I'd have to go all the way over to 81 to get to a height of 4. The other direction, I'm going to be at 1/3 on the x and then down 1, where I'd be 1/9 on the x, very close to the axis, and down 2. 1/27, so really hugging the line, down 3. And I can see very clearly that I get a graph that looks like this. I had a horizontal asymptote at y equals 0. Switching x and y, that became a vertical asymptote at x equals 0. And we can also see that it is a reflection across the line y equals x. This, of course, is the graph of a logarithm. What logarithm is it a graph of? Well, let's go ahead and do what part C says. Let's find the inverse algebraically. So if I take f of x equals 3 to the x, I'm going to first rewrite as y equals 3 to the x. And now I'm going to swap x and y, because that's how you find an inverse. We just did that. We swapped all these x's and y's. So I get x equals 3y. 3 to the y, excuse me. Okay, so this is technically the inverse right here, but we don't usually write things in terms of x equals. So let's go ahead and further simplify. And the way I can do that is by rewriting this as a logarithm, because a logarithm will get the exponent all by itself. So what logarithm would this be? It's base 3, so we're going to have log base 3 of x equals y. Or in other words, the inverse of f is equal to log base 3 of x. And that would be this graph. All right, so that's a logarithm graph. This is the parent function of a log base 3 graph. And just like exponent, when it's 3 to the x versus 4 to the x versus 5 to the x is very predictable, well, that'll translate just as predictably over to logarithms as well. And that's kind of what we're going to spend a little time looking at. So if I made a table of values for y equals a to the x, then we know, see, I'll do -2, I'll do -1, 0, 1, 2, maybe even a 3. A to the 0 is 1. A to the first is a. Plug in 2, I get a squared. I get a cubed. A to the -1 is 1 over a. This would be 1 over a squared. So if I graph those points, I've got 0, 1 over 1 up a over 2 up a squared over 3 up a cubed 4a fourth, 5a to the fifth. Very, very predictable. This point, of course, would be -1 and 1 over a. Then we'd be further over and we'd be at -2, 1 over a squared. Again, very predictable. We could go way over here to -10, and the y value would be 1 over a to the 10th. All right, so then what does y equals log base a of x look like? A would be the exact inverse. So let's just swap our x and y. So our domain of 1 and our range of a gets swapped. So now I have a1. I have 1 leads to 0. 1 over a leads to -1. 1 over a squared is -2. A squared is 2. A cubed is 3. A to the 5th would be 5. A to the 100th would be 100, right? Very, very simple and predictable. So if we graph those points, we just get this point here, which is 1, 0. We go over A and we get to a height of 1. We go over A squared and we get a height of 2. We go over 1 over A and we're going to be down at -1. We go close, super close, 1 over A squared. So we are probably super close to the axis. And that would get us down to -2. And so I get my graph that looks like this versus this. Okay. Hopefully this all makes sense. All right. Very predictable graphs. So here's what we know about logarithm graphs. Based on the picture we just drew, it looks about like that. Our domain is 0 to infinity. That makes sense because we have that vertical asymptote at 0. My range, I'm going all the way down. I'm going all the way up. It's going to take it a while to get up because this is going to be a slow grower, but it will eventually keep going higher and higher the further I go out. It's got no y-intercept. It has an x-intercept at 1. And then very common points again to find would be the point A1, base 1, whatever the base is, and 1 over the base, -1. So those would be the same 3 points that I want to see on exponent graphs, just the inverse of them on the logarithm graph. All right, let's do some quick practice. Let's graph y equals log base 3 of x. So when you get to a point where I'm at with this is very quick because you're thinking about the exponent graph, but you're not but you're getting better at just automatically translating it. So I know I'm going to be over 1, and I know I'm going to be over 1, 2, 3, and 1. If I want to keep going, I'd have to go all the way over to 9 to get to 2. Because this is going to be base 3, right? So this is 3 squared 2. This is 3 to the first 1. This is 3 to the 0, 0. And then I have the point right here, which would have to be 1/3 -1. And then that keeps getting closer to 0 and goes down to -infinity. So there's your standard graph y equals 3 to the x. Log base 3 of x, excuse me. It's after school, and I'm getting a little tired. All right, this one is shifting now, and shifting very predictably like they all do. It's going to shift over 4. So I'm going to shift my axis as usual, and I'm going to move it over 4. 1, 2, 3, 4, and up 3, 2, 3. So my new x and y axis is located here, and now I'm just going to graph that same picture, but from that spot. So I know I'm over 1 at 0, I'm over 3, and I'm up 1. I'm over 9. So 4, 5, 6, 7, 8, 9 total. And I'm up 2. I'm over 1/3 and down 1. I have my vertical asymptote now located at x equals -4. And my graph looks just like before. It's just shifted over and up. All right, let's keep going. Example 4. I've got negative log base 5 of x. So what does a negative do to the outside of the function? We know that that should simply just reflect it over the y-axis. Nope, x-axis. So real quick, if a logarithm graph looks basically like this, then when we flip it over, it's going to look like that. So I plug in 1, log base 5 of 1 is going to be 0. I'm going to go out to 5. 1, 2, 3, 4, 5. And normally I'd be at a height of 1, but I'm going to make that negative, so it's going to be at -1. I would normally have to go all the way out to 25 to get up to 2. So instead I'm going to be down at -2. And I would be at 1/5 and be down -1 normally, but that -1 is going to turn into a +1. And so what I end up getting is my graph that looks like this. Okay, example 4, B is a little trickier because I have this same scenario where, oops, I don't have a negative. I have a negative on my coefficient, and it needs to be a +1. So I'm going to take the time to factor this. But that factoring is still going to be inside the logarithm. And I get x -3, -2. Okay, so this negative compared to the previous one is not on the outside. I also have no way of taking it outside of the logarithm. That is impossible. So I have to deal with it as it is. So let's just do a quick examination. What's going to be the difference between doing log of negative x compared to log of normal x? Well, log of normal x, I plug in 1 and I get 0. I plug in, oh, I should put a base on this. Let's do base 5. I plug in 5 and I get 1. I plug in 25 and I get 2. Everything's great. But now, when I plug in, say, 5 for x, it turns into a negative 5. And what is that asking? 5 to what power is negative 5? And that is impossible, because the answer of negative 1 doesn't work, because that just flips 5 into 1/5. There is no way to take a positive number and turn it negative. So suddenly, all the x values I was going to normally use don't work. But now what will work? Now plugging in negative numbers will work just fine. So if I plug in negative 5, I get log base 5 of negative negative 5, which is 5. So if I put in a table of values, I plugged in negative 5, I'm going to get the same answer as if I plugged in regular 5 to normal log. In other words, I get 1. So what's this going to do? Instead of, sorry, this is getting a little bit sloppy. I'm really getting a little punchy at the end of the day here. So normal log base 5 of x looks like this. And so what's this going to do? The answer that's normally over here at 1 is going to be the answer at negative 1. And this point out here, which is normally 5, 1, is going to be over here at negative 5, 1. In other words, we have reflected across the y-axis. So the negative on the outside reflects it across the x-axis. The negative on the inside reflects it over the y-axis. So what is this graph going to look like? We're going to shift it over, and then I should expect to see a graph that looks like this. So let's find it. I'm going to move over to positive 3, 1, 2, 3, and down 2, 1, 2. So here's my new x and y axis. I have a vertical asymptote right here. I've got my x-axis. This is not an asymptote. It's just a guideline. So normally, I would graph this point at 1, and I'd go over 1, 2, 3, 4, 5, and be this point here. So I'm just going to now reflect those over and go the other direction. 1, 2, 3, 4, 5. And I have my asymptote going down. And that should be my answer. Okay, it's time to kind of wrap this up. We're going to talk very, very quickly about 2 special logarithms. And the first one is called the natural log. Natural log just means, and it's written as ln of x, it just means log base e of x. So you see ln of x until you feel comfortable, your brain should think log base e of x. And we already mentioned this one. Log base 10 of x is called a common log. And it can be written without a base. So you see a log without a base attached, it just means log base 10. That's kind of like this symbol right here, without anything on it, means take the square root. If you have a symbol on it, it means cube root, right? So it's sort of the same thing. Without it there, it just means log base 10, and that is the common log. So if I asked you to graph the natural log, it's nothing new, it's nothing different than what we just did. In fact, in a way, it's going to be easier. Because if I'm going to keep it exact, I'm just going to use the labels. And here's what I mean by this. If f of x just means log base e of x, then that means my points are going to be at 1, just because they always are. Because this would be me asking, like if I make a table of values, and I plug in 1, I'm asking you what is log base e of 1, which means what? E to what power is 1? And that would be 0. So we've still got the point 1, 0. So now if I plug in x is 2, no, I don't want to plug in 2. I'm going to plug in x is e, 2.718. Now what am I doing? Now I'm doing log base e of e. Well, that's 1. I'm going to plug in e squared. I'm going to get 2. E cubed, I'm going to get 3. 1 over e, I'm going to get negative 1. It's the same thing I would do if it was log base 5. It would be 5 squared is 2, 5 cubed. This is just e. Same thing, same concept. So I'm going to go over approximately e, which is 2.718. 1, 2, and right there. And how do I make it accurate? I'm going to tell you what point it is. It's E1. And then I'm going to go over 1 over e and down to negative 1. 1 over e is around a third, right? But how do I make it accurate? I just tell you what I did. It still has our vertical asymptote at 0, like all logarithms, and I get my graph. How do I know what my next point is? It's going to be over e squared and up 2. Next point after that, it's going to be a lot further away. It's going to be e cubed 3. E to the 10th, 10. Okay, g of x is going to be the natural log of negative x. And based on our conversation just a moment ago, that's just going to reflect it across the y-axis. So I'm going to have this point and this point and this point and this point down here. Oops, that's a little sloppy. I'll roll with it. So this is going to be negative e1. This is going to be negative 1, 0. This is negative 1 over e, negative 1. This point over here somewhere would be negative e squared, 2. This is g of x. And h of x would be, let's go green. H of x would just be a reflection over the x-axis. So it would be the red reflecting to the black. Okay, hopefully this is helpful. It was a little bit quick and I misspoke a few times, but I think we got there in the end. If you have questions, let's talk about it in class.